C43, if you learn in math class, I don't know, I forgot about it. I learned this about 25 years ago in the high school. Okay, what's the final number? 64. So there is a 64 theoretical possibility of the genetic code. But how then we use it? We use only 61. How about these three? These three are responsible for a stop code. For the stop of the translation. What are they? It's UAG, UAA, and UGA. This is, I always make a joke, this is University of Georgia called UGA. It's a very good school in my area in food microbiology. So, it's stop code. Okay. We also call it a nonsense code. Okay, nonsense code is the same thing. Now, start almost AUG. Okay, 61 genetic code translated how many amino acids? 20 amino acids. Okay, how come? It should be 20 genetic code, is that right? How come there's 20 amino acids? There's a little bit redundancy, is that right? And we have a special terminology for that. I'll make sure my spelling is correct. This is called. I want to mention. I want to make sure my spelling is correct. Degeneracy. Degeneracy. Redundancy, the same as redundancy. Okay. Now, why they can do that? We have a 3 box. They are very picky for the letters and the genetic code in the box 1 and box 3. They give you flexibility or flexible for the box 3. And this phenomenon, we call it a wobble. So give you an example. Let's say arginine. Can you see ARG? CGU is arginine. And CGC is also arginine. And the CGA is also arginine. CGG is also arginine. So that could be anyone. That's what a wobble phenomenon. Now, it is very important. Why? Because during the translation, and even replication, they're going to have some error going to come out, more or less. This is like you in the, during the exam questions, very few, you get 100. Is that right? You're going to make some mistakes, same for those bacteria. And they will be more strict for the position 1, position 2. But for the position 3, they let them make some errors sometimes. Okay, this is good for them, to have some flexibility. We all like flexibility. We don't like mandate, is that right? So, that's true for the bacteria also. So these type of thing also happens, and we call it a mutation, and these things we call it nonsense mutation. So nothing will be impact the final function, the final amino acid sequence. Okay, so this is what I want to mention. This is a good example for a wobble. Okay. Now the next one is I want to mention. This is we talk about the tRNA. Okay, that's going to carry on amino acid. Then how do you know it is a tRNA? I'm going to do experiments. I have tRNA, mRNA, all RNA combined together. So I do the centrifuge. And I'm going to be isolated there. How do you know it is tRNA? Hard, is that right? When you look at the structure, you will find in the tRNA, there is some of I call it weird gene base. you have a T theta C, you have a theta, you have a PY, PU, those type of very weird genome. So if you see a genome isolation, you see the gene base have those very weird gene base. Instead of that, you have AUGC, or in addition to AUGC, they're very possible that is TRNA. And they are carry on amino acids on the top side, on the 3 accept ends. The synthesis need an enzyme. That enzyme we just mentioned, amino acetyl tRNA synthesis. And on the bottom, you see the anticodon, the bottom, which is carry on the anticodon. Okay? So if you want to draw a picture of tRNA, we can draw right here. The tRNA, very simple. It looks like this. Like a tree. It's like a tree. Here you're going to see T theta C, PY, PU, those very weird gene base. On the top, this is always will carry on amino acids. And right here, it will be carry on anticodon. Now what is anticodon? That will be the complementary codon to mRNA. That will be the anticodon for the genetic base, the 3-letter codes. So let's say AUG. This guy will be UAC, very possible, for the tRNA. Okay? So this is some basic information we want to give to you. Then we're going to go ahead and talk about translation, how that works. So I try to keep transcription right here. We're going to try to write the translation will be right in this form. So we're going to talk about this translation. Okay, translation you need to know. There is a place going to happen the translation, which is the ribosome. Okay, what is that? What it looks like? Do you still remember? 2 subunits. The total is 70S for bacteria. Okay? How about the top? 50S. The bottom, 30S. Okay, we're going to talk about that. Same thing. Initiation, elongation, and termination. I want to talk about these one by one. Number 1. Once you have a ribosome, at the beginning, the 50S and the 30S, they are actually separated. Okay? This is 30S subunits. These 30S subunits, I try to maintain a status which is separated. So there is something going to be attached to the side of the 30S subunits of the ribosome. That is called initial factor 3. Okay? Then I'm going to do something. I'm going to start to do the translation. This is the initiation. Now, of course, you know, there is an mRNA going to go in. Okay, this mRNA going to come in. Sorry, let me draw this a little bit down. Okay, so we have the subunits right here. This is 30S. Okay, this 30S is being attached by initial factor 3 to maintain the status. Now, I have an mRNA going to come in. This is mRNA. This mRNA is not, we are saying, any mRNA will start to do the translation. They'll have some of the special sequence also have to be recognized. Because we always have start places. The mRNA have to have a very special sequence right here called AGG. AGG. This is called SD sequence, called Shy Dagano sequence. This SD sequence has to be recognized by 16 sRNA as major components of the 30S. Then it will start to do the translation. You must have that one, AGG. Okay. Once they started to combine, what are we going to do? Something going to go here. This is called, remember we just talked, tRNA going to go here. Okay? This is tRNA. This tRNA carry on anticode, let's say AUG, not really AUG. Okay, the anticode will be U, what? AUG, UAC. And on the top, this is always called, the first one is FMET. What is that? That's called a formal measurement. Okay. At the beginning, they need a formal to do some of the modification. Or formula, sorry, it's a formula modification. Messaging. This formula will be initiated there, but later on, when the translation starts, it will be hydrolyzed. So this will be hydrolyzed later. Okay, so they're going to be coming. But they are not going to come in just by themselves. They are going to come in to carry somebody. Somebody going to carry them. Which one going to carry them? Elongation factor 2. So the elongation factor 2 carry on the first tRNA. Also, when they carry on, you go to some new places, you need to prepare money, is that right? They also carry on something else, which is GTP. This is something you drive a car, go to a zoo. You need to prepare some money on the pockets because you're going to go there. Or let's say we have a boat, okay? So what's going to happen? This guy goes here. Once this guy goes here, what happens? This big subunit is going to be packaged. Come from somewhere. This is called 50S subunits. This 50S subunits, there is an important construction, 23 sRNA. Why it is important? There is a transferal enzyme will be transferase, will be play important role later on. Okay, so this is the initiation of at the beginning. Okay, now we're going to mention is elongation. What will happen for the elongation? So we're going to draw like here. $50S, 30S. This one is already there. That's MIA. Okay? Now remember, once the package, you have a 3 location here. For easy understanding, we gave them 3 names. EPA, so easy. It's not Environmental Protection Agency. We talk about it every day. No. Remember we talk about climate change, fossil fuel. We talk about EPA every day. You see the news every day. Is that easy to remember? It's also EPA, but it's not Environmental Protection Agency. What does the E mean? Exit site. What's a P means? I'm going to write this on the side. Okay. What's the E means? Exit site. For the free RNA, for the free tRNA to release. What is the P site? Peptide site. What is A site? Amino acido binding site, or we say amino acido site. So what going to be it looks like? I just give you an example, okay? On the P side, let's say you have a FMET goes there. Then something will be, the tRNA will grab some amino acid 1, will go there. Then they start to move this direction. So in the next stage, what's going to happen is subunits. Okay, this is mRNA. This is the same thing. We have EPA. What's going to happen? This one, after finish the job, they're going to go to the E place, ready to flee away. And the P side will have a new one coming. That's called amino acid 2. Now, how about the A side? Sorry, this goes here. This will move there. This will have amino acid 1, and the NET goes here. Okay. Then there's a new one going to come in. Amino acid 2. Okay? Now once you move to here, what's going to happen? Subunits right here. This is goes. This is the mRNA. You have EPA. This is going to release. This is gone. Okay, then they just start to move. In here, you will see this guy is going to be longer, become MET, AA2, AA1, and then you have a new AA3 comes. So move on this direction. And when this amino acid sequence is always from C prime to the M prime. Okay, so they do this moving. Later on, how do we know it is finished? How do we know it is going to be termination? Because they see the stop signal, which is UAA, UGA, and the UAG. And then what's going to happen? These two will be released separate. This is 50S, this is 30S, and this guy, the elongation factor 3, put it back. Now here I forgot to mention, I mentioned earlier, this elongation initiation factor 1 will be attached, So this will be removed when it's. Now, once the initial factor 2 has been transferred there, they will be released, and also this GTP will become GDP and PI. Okay? Because they pay the money, then they go to find a new one, then they continue to do it. Now, during here, what's the story they're going to happen? There will happen 3 things, which is amino acido tRNA synthesis of amino acids. Number 2, what happened? Between these sections, so what happen is transpeptidation. Transpeptidation. This rely on the enzyme, which is right here. So that's rely on 23 RNA transferase. This is underneath 50S units. So the last one will be happening is translocation. Okay, so that's going to be the whole process going to happen. So we have a slides right here. FMET, amino acid tRNA. This is the anti-codon. Okay, transfer RNA, always the anti-codon. Ribosome, remember? And the first one is always FMET. Formylmethionine tRNA. And this is initial places. Remember, diagonal sequences right here, AGG. Very conservative. That's what happens, is what I draw right there. This is well explained to me. And the one thing I didn't, I always mention everything. When they do, this is carried on by elongation factor 2. Okay, once they finish the job, this elongation factor, so we're going to keep that out. And then goes here, they pay the money, so hydrolyze become GDP, and then the 50S going to package that. And this is a kind of the elongation. 3 things happen: amino acid tRNA binding, transpeptidation, translocation, and we have a 3 site, peptidotide site, amino acetyl site, and E site, exit site. Okay, finally, what happens? You see a stop code. UAA, UAG, UGA, and you have a release factor, don't forget about it. So release factor. 1, 2, 3, then they're going to be released. Okay? If you don't understand, you can look at this. Can you see it? This is 1, you go in there, then you transfer there. Okay, go here, go here. You go here, this MET is go long, all the way. Okay, 6, goes 7. This is kind of confusing because the figure is 1, 2, 3, 4. Okay, 1, 2, 3, 4. Yeah. 1, 2, 3, 4. 5, 6, 5, 6, 7, 8. Goes 1, 2, 3, 4, 5, 6, 7, 8. So that's why I didn't put this one at the beginning, because it's kind of confusing people. Okay? When they go here, then they attach to there, then at the end. FMET is always at the end, then you go here. Okay, there's another one coming, then they're joining. So join goes here. Yeah, the join goes here. Actually here, we should write this one. They're going this way. Okay, so this is 1, this is 2. They're going this way. So this is always, if you want to write, it's FMET, AA1, AA2, AA3. Okay, it's like that. It's like it goes this way. Okay? See, the FMET goes that way. Then later on it's going to release. So This is the one little bit confuse you, but it's okay for you to understand it. Okay? Let me see what's the time. Okay. We finished talking about here. We talk about transcription, translation, and everything is here. And we draw the picture here, and I'm going to take a picture of this one because I want to upload onto the eCampus so you guys can read it. And but I want to mention something else before Jessica talk about it. Okay, so I'll just take a big picture of everything what I drawn there and put on the eCampus, and you guys can read. It's like a notes, so it's like another class notes. Okay. This is a microbiology class. It's not a genetic class. So we want to talk something else related to microbiology. And I want to be moving this off. And just on this corner, we're going to talk about. And you pretty much already know, but we want to mention something related to the microbiology. We finished talking about the translation, transcription. There is something we want to mention. There is a difference between bacteria and eastern modes. Why? This is prokaryote. Prokaryotes. And this is the eukaryotes. So that's different. First of all, if we look at the notes very clearly, prokaryotes is polycystronic. Eukaryotes is monocystronic. One of them is monocystronic. It's very simple. Okay, let me just using different color to do it. You have this sequence like this. You have a, we call it a trail part. You have a leading part. This is a coding part. Then you go this way. Has amino acids comes out. So basically we say, one gene, one protein. How about bacteria? Bacteria is a little bit different. Bacteria is you have